Hi everyone, my name is Isabela Santiago de Matos. I'm a postdoc at the University of Portsmouth in the UK, and I'm going to talk about using gravitational waves as tracers of large-scale structures. I will start by discussing what are the effects of dark energy that can be probed from gravitational wave observations. Then I will talk about the Peak Sirens method. This is a method based on gravitational wave galaxy cross-correlations to probe the Hubble diagram and also dark energy properties. And then I will talk about my recent work on the first measurements of gravitational wave galaxy cross-correlations. Effects of dark energy on gravitational waves. So first of all, the gravitational wave signals that have been detected so far, they are transients emitted by binaries of compact objects like black holes and neutron stars. The important thing here is that the signal that is detected has an amplitude that falls with the distance to the source. And therefore, when you detect those signals, you can measure the distance to the source, just like with standard candles, but here for standard sirens, you don't need a calibration with other probes. So if you could know the redshift of these sources, you could in principle probe the Hubble diagram. So the distance, the luminosity distance redshift relation, that depends on the Hubble constant, but it can also be affected by dark energy. The main problem with standard sirens is that it is not easy to find what's the redshift of the source of a gravitational wave. This information is totally degenerate in the gravitational wave waveform with the combination of the masses of the system. And so you need to use either extra assumptions or additional data sets to infer the redshifts of those sources. So the easiest way to do that is when you have a bright standard siren or a multi-messenger event. In this case, if you have an electromagnetic signal that is emitted by the same binary source, then you can measure directly the redshift from this electromagnetic signal. That happened just once, however. So these events are very rare. Most of gravitational events, they're emitted by binary black holes, and electromagnetic counterparts are either in existence or difficult to measure. And these are called the dark sirens. So for the dark sirens, what is currently done more standardly in literature is to assume some function for the mass spectrum of compact objects, and that will give you some information indirectly on the redshift of sources, and use a prior that is built from a galaxy catalog. Because compact objects, they live in galaxies, and so if you know what are the galaxies in the same sky position of the gravitational wave, you can have some prior information on the redshifts of those sources. So that's the more or less standard approach. The Hubble diagram that one can build with standard sirens is, however, slightly different from the one that you can build with luminous sources, where you measure the luminosity distance. In fact, the gravitational wave distance is not the same as the luminosity distance. It is a function of redshift, that is the function I'm showing here in this slide, which has the effect of dark energy enters in two ways. So on the very right of the equation, you have the dark energy density. And so you have, whenever you have an equation of state for dark energy, which is not just for a cosmological constant, you will have some effect of dark energy there. And that is the same that you probe with luminous sources. And then you have an additional effect, which is this function on the very left of the equation of the right-hand side, psi of z. And this function, it's called the gravitational wave friction. It's measuring the ratio between the gravitational wave distance and the luminosity distance, such that in lambda CDM this is equal to 1. And it is present in most of dark energy models that have been studied. Most models, they have conformal couplings, for instance, and these would generate this gravitational wave friction. That is, for example, in Horndeski gravity, this function is measuring the time evolution of an effective Planck mass or an effective strength of gravity over cosmological scales. Bright sirens can be used to probe this distance redshift relation, as I've shown before. So even if so far we have detected just one of these events, with future detectors like the Einstein telescope or Cosmic Explorer, called the third generation detectors, These events are expected to be seen to the hundreds or even more. And so many forecasts have been made for how well we can probe this quantity. Here I'm showing one of them. So if you combine these future distance measurements from gravitational waves with other distance measurements that are also going to be available at this time from supernovae and from angular diameter distances, you can probe this psi of z in a very model-independent way. So without having to assume any expansion history, h of z, or any specific dark energy model. And so you can see in the blue and magenta curves, they are showing here the lower bounds that we are going to obtain on this function. And they are at the percent level for a wide range of redshifts. If you then move to specify a dark energy model, then you should look at the gray curves in this plot. So the dashed gray curve shows here a specific dark energy model that is not ruled out by data currently. And the continuous gray line shows a dark energy model that is going to be ruled out by this data. Just to say that there will be a 2 order of magnitude improvement from current observations with those facilities. Okay, but I said that most gravitational wave events, they are actually not bright sirens. They will continue to be dark sirens. And so a lot of work has been done to actually take in cosmological information from those data. What I will present now is the Peak Sirens method. So it's a method to use dark sirens to also trace the Hubble diagram by optimizing their overlap with the galaxy distribution on very large scales. So this was a method that has been initially introduced in around 2016 by a few papers and later was worked out in our group in this work led by the student João Ferri. And the method is about looking at which redshift slice the angular distribution of galaxies maximally overlaps with the distribution of gravitational wave sources on large scales. So more precisely, if you have these two 3D maps of large-scale structures, one being the distribution of gravitational wave sources on the sky, so their angular positions and their distances, and for galaxies, you would have their angular positions, but their redshifts will be their radial coordinate. Then you can look for the maximal overlap of these two 3D maps. You can split these maps into spherical shells, so tomographic bins in each of their respective radial coordinates, so redshifts or distances. And you can compute the 2-point function between any of those pairs of spherical shells. You can project then this 2-point function into spherical harmonics and compute an angular power spectrum, which is now a 3D quantity. This angular power spectrum looks like this. So this plot on the right here shows an average over thousands of simulations that we have done for 3G detectors. You can clearly see that the angular power spectrum at each scale, it has this feature, this peak that you can see in this plot. So for the gravitational wave sources at each specific distance, there is a redshift of the galaxies where they maximally correlate with those galaxies. So the position of the crest, it tells you what are the redshifts of those gravitational wave sources at that distance, and therefore what's the distance redshift relation. What we studied in this work was how robust the position of this peak is to several physical effects. So you can show what's the impact of weak lensing, for instance, and on the existence of the true host galaxies of the gravitational wave sources in your galaxy catalog. You can show that this is not that this doesn't change this observable. And further, you can show that the position of this peak doesn't depend on the precise details of the matter power spectrum. So it doesn't depend on the details of the large-scale structures, but rather on the matching of these two structures. And this is because basically the matter distribution in general in two different redshift slices is quickly uncorrelated with each other. And so you can see some plots here that are showing the impact of on the shape of the power spectrum on the position of that peak. So on the left, if you see that if you produce simulations where you have a different fiducial cosmology in the construction of the power spectrum, but you do get right the distance redshift relation, then you recover the true cosmology of the data, even if this cosmology is very far from the one of the power spectrum. On the right, you see a bit of the same thing. So if you change in your simulations the modeling of the nonlinear structure, if you completely remove, for example, halo fit corrections, you still recover the correct cosmology because the distance redshift relation is the same. In terms of precision of this method for cosmological inference, we forecasted that with 3G detectors, we are going to obtain sub-percent measurements of the Hubble constant from this Peak Sirens method alone. So before combining with any bright siren or even with other methods for dark siren cosmology. So that's really promising. Of course, that will come in a decade or so. And so we've also forecasted the capability of the next few years of data from current detectors. And we found that this will already give a few percent measurement of the Hubble constant from this data. And then moving to dark energy, which is the main topic of this conference. We've also forecasted what's the power of these peak sirens for W0 WA, so for the dark energy equation of state. And this is the plot you're seeing here on the right. So the numbers are roughly similar in terms of precision of what you currently have with the DESI latest results. So that is going to be a complementary test, but it's not going to drive probably these constraints on W0 WA. That is, of course, not the same one can say about the gravitational wave friction. The gravitational wave friction, which we did not forecast yet with Peak Sirens, it is so the distance redshift relation for the standard sirens is much more sensitive to gravitational wave friction than to W0 WA. So that's probably where standard sirens are going to be more informative about dark energy. On my more recent paper, we have investigated if it's possible to apply this peak sirens method to current data already, if it's possible to already detect this peak of cross correlations with current data. And the current data has several challenges because there are very few gravitational wave events which are localized to a very small area in the sky. And so the best localized gravitational wave event is called GW190814 and is localized to 18 degrees squared, which is quite large. We decided to use the galaxy catalog called GLADE Plus, which is the galaxy catalog that is being used by the LVK collaboration for other dark siren methods. So we wanted to use this catalog for comparison. And that also restricts quite a lot the gravitational wave events that we could have used, because its catalog is not very deep. And so at the end, we used 2 gravitational wave events, the bright siren, for which we completely ignore the redshift that is known for this event, because that's what we're going to measure with Peak Sirens, and the best localized event, GW190814. Correlating these two maps, the GLADE Plus and the probability density maps of gravitational waves positions, we found those angular power spectrum that you can see here in this plot. So you can see clearly that at 2 different distances, around 250 megaparsec and very low at the 40 megaparsecs, you see that the correlations say peak at a specific redshift. Just like in the previous plot that I showed for 3G detectors, as if we had cut 2 horizontal slices of the plot on the left to put on the right. And so already with current data, we could study these cross correlations and demonstrate that there is statistical significance for the position of this peak at various multiples. So the way we approached this problem, just like in our previous work, was by doing simulations. So we performed tens of thousands of light cone simulations of galaxies using the cold glass by including various realistic aspects of data like selection effects, photometric redshifts, etc., to mimic the maximum we could the Glade Plus catalog. And on top of those simulated galaxy maps, we generated gravitational wave maps. So we pick host galaxies from these galaxy maps and mimic the same gravitational wave probability distribution that comes from the gravitational wave posteriors on top of those galaxies. Then we compute the angular power spectrum, the angular cross spectrum, sorry, between these pairs of maps and their covariance. So the covariance here is going to be extracted directly from simulations. Another ingredient in our analysis is the gravitational wave bias. So the gravitational wave bias is just like the galaxy bias, is measuring how much the gravitational waves are tracing the clumps of dark matter on very large scales. That quantity is very interesting for astrophysics because the gravitational wave bias tells us where and which environments gravitational wave sources live, how dense are those environments. And ultimately, that is connected to how compact binaries form. And this is a core science case for gravitational wave facilities today and also for the future ones. So the gravitational wave bias here, it impacts the amplitude of our signal, the amplitude of those cross correlations. And therefore, it will be one of the three parameters in our analysis, both H0 and gravitational wave bias. We've also performed simulations where we build the galaxy and gravitational wave maps, which are uncorrelated. So they are built from different realizations of dark matter field. And using those noise-only realizations, we could perform a null test and show how much more the data prefers to be described by these simulations where the maps are correlated versus the ones that are uncorrelated. That allows us to quantify a significance of detection of cross correlations of almost 6 sigma when considering the two events together. From this detection of the cross correlations, we could also measure the Hubble constant and place bounds on the gravitational wave bias. So that is the plot that you're seeing here on the left. You can see that the higher values of the bias leads to a more precise H0 because the signal to noise ratio scales with the bias. And you can also see, if you look at the upper panel, the comparison of the result for H0 with the latest results from the LVK for the dark silence method, the one that uses the galaxy catalog as a prior on the redshifts of gravitational wave sources, plus some information on the mass distribution of compact objects. You can see that these methodologies are giving comparable results at this point. However, the dark silence method is heavily relying on the mass distribution of compact objects, which is also an open question, an open science case for gravitational wave observations. If we had 100 events like the best localized event so far, we can expect that we would measure H0 with around 4% precision. And that is in agreement also with our previous forecast for the next observing runs of the LVK. And so to conclude, I would like to say that standard sirens, they are a unique probe of dark energy properties, and especially the gravitational wave friction. So they are a much cleaner way of probing conformal couplings than what you can currently do with galaxy surveys. And future data is going to provide percent level measurements of this property of dark energy models. Second point is that cross-correlating gravitational wave sources and galaxies provide a cosmic ruler, providing a model-independent reconstruction of the Hubble diagram. And this Peak Sirens method has also the advantage of not relying on complex and unknown astrophysics of compact binaries. That is already a science possible for the current data, but only at the 3G era we will have really high precision on all these parameters. Thank you.